In this lecture, I want to look at a mechanistic nuance related to the E2 reaction. It's an important detail as you're looking at more sophisticated examples of the E2 reaction. It's not going to have too much bearings for the scope of this course, but again, it's important later, and it's actually introduces an important concept that's useful to understanding more advanced elimination reactions. And so what I want to do is just bring in front of us the E2 reaction again. So let's do an E2 reaction with this molecule and LDA. So in this reaction, we have only one vicinal hydrogen. So here's the carbon with the halogen attached to it. And then adjacent to that is a carbon that has only one hydrogen atom. Everything else is a little too distant or too close. So the LDA is going to engage the vicinal hydrogen, push the electrons over to make a new carbon-carbon double bond, and push off with the third arrow, the leaving group bromine atom, to give rise to this product. Now, what I want to do is introduce a concept called the anti-periplanar arrangement, because it's relevant here. The E2 reaction requires anti-periplanar or an anti-periplanar arrangement of leaving group X and the vicinal hydrogen. And so here's another example where pictures are worth thousands of words. And so what I want to do is just kind of show this to you instead of trying to explain it with words. The words that are important are saying that you need to have this for every E2 reaction. And then the picture will be helpful for understanding what the new concept is, which is this anti-periplanar arrangement. Okay, let's take the starting material that we just drew and consider a Newman projection that's analyzing this bond. Okay, so I want to consider a Newman projection. So stepping back a few learning modules now. We have a dot with a circle around it. Now, I don't have stereocenters, and I have not defined any wedges or dashes. So I get to pick what the groups are attached to either of the carbons across the bond to be analyzed. And I get to pick where the groups are. So here's our dot. It's the first thing to encounter our eye, then a circle. So the dot's going to have a bromine. Let's make this easy on us. And then additionally, no sense in considering a transition state structure for free rotation. Let's just go ahead and draw a staggered conformation. And maybe, I don't know, we have an H, a CH3, and a CH3. Okay, so the thing about the E2 reaction is that it requires an anti-periplanar arrangement. So what is anti-periplanar? So anti-periplanar means the groups are aligned opposite, and hence the term anti. They're opposite and within the same plane. They're opposite and within the same plane. And so same plane would be periplanar. Okay, now it turns out that for a stable Newman projection to exist, every group has a periplanar group on the carbon next to it that is anti. Okay, so anti is almost redundant, but let's look at the bromine atom. If we consider the bromine atom, the group that is within the same plane of it and is opposite to it is the CH3. So we say that here, the CH3 is anti-periplanar to the Br. We're going to focus on what's anti-periplanar to the bromine because that's the leaving group. But every one of these 6 groups shown by this Newman projection has an anti-periplanar substituent. Anti because that provides a stable staggered conformation. Periplanar because of the other substituents that are across from it on the adjacent carbon atom. It's the ones that are within the same plane that are of interest to us. Okay. So why is this important? Well, in the E2 reaction, or let's put it this way, the E2 reaction cannot occur unless the vicinal hydrogen is anti-periplanar to the halogen leaving group. Okay. So if we reconsider our Newman projection, I'm just going to redraw it. What I'm saying is that this conformation cannot do the E2 reaction. It has all of the requisite atoms to do the E2 reaction, but it's not until we do a 60-degree rotation of the back carbon, the circle carbon, it's not until we do a 60-degree rotation that we are able to do the E2 reaction, because when we do the 60-degree rotation, now the CH3s are gauche to the bromine, and the hydrogen that is, if you look, this hydrogen now with a star is anti-periplanar, and that hydrogen was the only vicinal hydrogen. And it's now, after that free rotation of 60 degrees, now it is anti-periplanar. So it's not until we do that free rotation and align the only, in this case, the only vicinal hydrogen to be anti-periplanar, it's not until that point that the E2 reaction can occur. And we could, for the sake of practice, redraw our products here. And so there's there's a really nice way of kind of analyzing this more deeply when we consider the molecular orbitals involved in formation of the product. But this is what's required for the concerted elimination of a halogen. So this is only required in the concerted E2 reaction, which is why I bring it up now. Okay, so in this video, what I've done is I've shown you what the anti-periplanar arrangement is and how that's required for a concerted E2 reaction. And I showed you that, you know, if the vicinal hydrogen to be deprotonated and the bromine to be lost as a leaving group are not aligned in an anti-periplanar arrangement, it actually can be shown with very sophisticated experiments that if they can't be aligned anti-periplanar, the E2 reaction will not occur, even if all of the requisite atoms are there. This has long-term consequences in other E2 reactions where more complicated E2 reactions with stereocenters. But for the sake of this lecture, we'll just stick with this simple example, and this will just be kind of a concept to keep in mind. We can look at more interesting examples with stereocenters where there's a direct consequence of the anti-periplanar elimination. But for every E2 reaction that occurs, they're all occurring with anti-periplanar arrangement or the anti-periplanar conformational state of the haloalkane starting material.